Okay, first, I'd like to thank organizers for giving me opportunity to this wonderful conference during 17 and Tel Aviv, and also this great opportunity of this 20 years anniversary of AdS CFT. So here I'd like to talk about procedure of the optimization of path integral, which somehow recover some ABS space-time from conformal field theory viewpoint. And this is a kind of continuous version of the conjectural relation between tensor network and AdS CFT correspondence. And this talk is based on these two papers. First one is a short letter, and this is a main paper which just appeared last week, and also related to this earlier idea, which is also our work. And the collaborators is Pavel Kapta and Nilay Kunduz, both are postdoc in our institute, and two graduate students, Masamichi Miyaji and Kento Watanabe. So let me start with the motivation of this talk. There are two motivations of this work. First motivation is the more main one, is what is the basic mechanism of AdS CFT correspondence. This is a very fundamental question, and I would like to give some one attempt to understand these difficult questions. And one intriguing idea which we'd like to focus on this talk is the conjectural relation. Already I just mentioned this is some AdS CFT, interpretation of AdS CFT in terms of tensor networks, started from the observation made by Brian Swingle. And this is closely related to the idea of the emergent space-time, emergent space from quantum entanglement, and where tensor network is originally defined as kind of a network of quantum entanglement which describe wave functional of quantum many-body systems and quantum field theories. And this, so in that sense, tensor network captures a sort of geometry of quantum state in quantum many-body systems. So the holography, so we can have a direct connection between entanglement and the area of minimal area surface. And if we look this closely, so we have some subsystem A, and which corresponds, and entanglement entropy for this region A corresponds to the area of this minimal surface. But if we look at this entropy formula, so it's like area divided by 4G Newton, and this is just generalization of Bekenstein-Hawking formula of black hole entropy, but we can rewrite this in terms of Planck length. Then roughly this formula tells us that so each Planck unit cell, we have 1 bit of entanglement or information, but then if we regard this as an entanglement, there are 1 bit of EPR pairs, 1 EPR pairs in each Planck unit cells. So if we just naively think about this correspondence, then one might expect that space-time in gravity might be captured as a collection of quantum bits of entanglement. So there are many EPR pairs, but we can choose this position, this surface A and B, and as we can move the position and also size as much as we like. And that sense, maybe space-time might be consist of entanglement. And this leads to the idea of this emergent space-time from qubits. And one explicit concrete realization of this idea, but in some kind of toy model, is look at this tensor network, which I summarize here. So this is the most prototype, most basic tensor network, which describes conformal field theory is a mirror network, first constructed by Vidal, 2005, and it's applied for AdS CFT by this Swingle's work. So this is a mirror tensor network. So we have a very complicated, so many spins at the bottom where we have some UV state, but this UV wave functional is interpreted and represented by this whole network. So we in the end up with just single spin, which is just trivial state without no entanglement at all. But we can have two procedures. So we have first one is a coarse graining. So we can combine these two spins into one by this triangle procedure. This is actually getting very important in my talk later. So this is a coarse graining transformation. So this is actually mathematically this is an isometric transformation. Another one is a unitary transformation. Just 2 qubits. We have 2 spins, and also get after unitary transformation we get 2 spins. This is a unitary transformation. So this is called entangler or disentangler. We cut it out some entanglement of ground state of many-body system and trivial disentangled spin. So combining these two, we get some network, and nicely this has a scale invariant structure. And if we look at some entanglement entropy, so we can estimate some entanglement entropy of particular part for this region A. So then entanglement just comes from these links. Always it's come from links. Sorry. So it's come from links. So we can have a maximum amount of entanglement should be given by, bounded by, minimum number of intersections between this curve, which surround A, and this number of links. So this is scales like log L because owing to this structure. So we have some first n spins, and next layer we have n over 2, and that way, after log L step, we end up with just single spin. So that sense, roughly we can estimate this entanglement entropy. So nice, this logarithmic rule is nicely agree with well-known result in 2D CFT. So this is a conjectural relation between AdS CFT and mirror. So basic key idea here is a tensor network corresponds to the time slice of anti-Doshita space. So because we are specifying particular state, which we fixed some particular time, so we don't see time direction, but we can see some space direction. So this is a basic idea. But this is a kind of heuristic idea, and after there are so many works which explore more details, and there are several questions raised, some problems raised, and here are some summary of the part of the question. So how can we see, for example, spatial conformal invariance? Scale invariance is obvious, but it's not that so clear. And also this construction itself is not isotropic because this triangle vertex here, this guy is not rotational invariant, even 120 degrees, not rotational invariant, so this does not fit nicely with hyperbolic space. And why also this entanglement entropy bound, which I mentioned, it's very heuristic, and it's why it is not clear why it is saturated. And eventually, so more serious, more sophisticated question, how can we derive Einstein equation, and where the sub-AdS space locality is very important. But nevertheless, there are very interesting recent developments, especially in lattice models, not continuum, but lattice models. So that gives some nice toy models. So some improved version of tensor network, the so-called perfect tensor network, or called happy model, and also random tensor network by these people. And that resolved this ABC in a discretized model. And so there are also other ideas. So we stick to mirror, but we can interpret mirror in terms of different ideas. So this is a so-called kinematical space, and mirror itself is not directly related to AdS, but it's some non-local transformation of that. So this is discussed by these people, and there are very interesting developments. So, but in this talk, I'd like to think about more to understand the genuine AdS CFT in so CF conformal field theory in continuum limit. So maybe by taking this continuum limit, we can solve some of these problems. This is our hope. And some of them, indeed, as I explained, resolved. And so motivated by this, we'd like to propose some new alternative approach based on the path integrals. So path integral is more familiar to a particular physicist and string theorist. And so this is also, of course, this is related to continuum limit of the description. And we have some nice connection between path integral and continuum limit of tensor network, as I will explain. So this is our approach. And there are we have several guiding principles. So guiding principle, number one is here. So the idea is here. So we have in mind some tensor network, but we are interested in minimum tensor network, which is most efficient algorithm to calculate some ground state or some state. In that sense, we cut it out some unnecessary tensors and want to shape up the tensors. And this is, in other words, we want to find some most efficient tensor network, so which we call, this is our language, but we call this is optimization of tensor network. So we want to shape up tensor network and just want to find some best one. And our hope is to relate this procedure, so optimization of tensor network, is related to the solving dynamics of gravity, namely, in particular case, of which is a holographic CFT, this is, of course, solving Einstein equations. So we have some phenomenological argument which we have this kind of relation, as we will come back later. So this is the first part of motivation. And second part is complexity. So this is computational complexity. So recently, there are very interesting developments of complexity, especially from holographic side. So there are holographic formulas proposed by several people. So for this, I think tomorrow we have some several discussions by Brown talk and Meyer's talk, and we're looking for that. And so, for example, there are two conjectures. Complexity is equal to maximum volume in anti-de space, conjectured by Stanford and Susskind. And also, complexity is described by some gravity action, Einstein-Hilbert action, in Wheeler-DeWitt patch of AdS, proposed by Brown and collaborators. And also, there are some boundary contribution, as pointed by the very interesting paper by Luna and Myers, collaborators. And so also, I'd like to mention this quantity complexity is definition of complexity is summarized here. This is a heuristic summary. But we want to create some complicated state, like some ground state of very complicated Hamiltonian. So we want to construct this state from trivial state, like, for example, just direct product state. So we act many unitary, this small unitary. So we act unitary transformation, for example, for two spins into two spin, and many times, then we get very complicated some state, complicated minimal systems. So how many times we have to act such a unitary transformation? And minimum number, we have to also optimize such a network. So then quantum gates, then the minimum number of this quantum gates or unitary transformation is called computational complexity. But for our purpose, we have also network in terms of tensor network language. So then we want to count the number of tensors. So this is, we take a minimum of that. That in other words, this optimization tensor network, and we shape up, then we can count the number of tensors. So this is a complex computational complexity in our viewpoint. So this motivates us to consider, so this quantum field theory counterpart of this quantity, and so for that we introduce a quantity which we call path integral complexity. And there, our guiding principle number 2 is here. So we have some lattice, originally it is some discretized tensors, lattice tensors, or also path integral we can think of just discretized path integral. So for that, actually we can naturally introduce the idea of the background metric. So for this kind of discretization, a lot of lattices, but this is obviously flat space. But we can somehow coarse-grain some of lattice. We can just hold many lattices, but combine to just one lattice. And for each lattice, for each cell, we just associate one unit length. So this is unit length area, unit area. Then we have obviously curved space. So this is much like, for example, hyperbolic space. That way we can associate some background metric. So then we can have some continuous description. And the second point is that, so we have to formulate what is the optimization. So for that, it is good to have some quantity, which we call I psi. So we fix some particular quantum state, and we define such a quantity. And in terms of this metric, which we have, changing the metric corresponds to changing the discretization and somehow shaping up tensor. And we claim this minimizing such a quantity with respect to metric gives the most optimized network. So this is of course, we have to explain how we define this, and especially in two-dimensional conformal field theory, as I will explain, so we have some nice candidate in terms of, for example, Liouville action. Okay, so these are guiding principles, and these are my contents of my talk. So we got some main formulation and application to entanglement wedge, and so also mention about some application to SQK model, but also higher dimensional conformal field theory. So, okay, so this is so let me talk about this our formulation. So basic rule is to simplify path integral such that it produces as a correct ground state, also correct UV wave functional. For that, we consider some 2D CFT. So for simplicity, so Z is a Euclidean time and X is the space direction. And deformation of discretization, this deformation of this discretization in path integral is, as already mentioned, it's somehow thinking about some curved metric such that one cell equal to has a unit area. So in that sense, anyway, we can naturally introduce some metric of this form, and in 2D, we can just factorize. We have some wire scaling, and up to this diffeomorphism invariant, we can just take a diagonal form. So this phi is a very important ingredient, and the original flat space metric is given by this. Epsilon is a UV cutoff, lattice spacing, and epsilon goes to 0. So metric divergent because so many lattices are originally we have. And we somehow have some change the metric so that this volume also changes. And so this is the idea of this optimization path integral. So we start with this kind of very dense lattice, almost flat, obviously flat space, but we coarse grain. So this is so here we have some UV state here. So initially, this infrared we can talk about very coarse graining, but in the end we end up with very fine graining of this lattice. But this procedure is also motivated by the recent interesting progress of tensor network, so-called tensor network renormalization. This is by Ivan Lee and Vidal a few years ago. So this is actually gives some nice optimization of tensor network. We start with, we rewrite the Euclidean path integral in terms of this square lattice tensor network, and gradually we coarse grain each lattices, we remove many tensors and end up with actually mirror network. So this is, we expect some continuous version of this. So this wave functional for conformal Fuseli vacuum is given by, so this is just standard Euclidean description of wave functional. So we pass integral from -infinity to t z equals 0. So this is we project down to ground state. And then, so an important point is that we can change the metric. Here we introduce a curved metric. So if we perform some Weyl transformation, so, but the original theory in CFT is originally conformal invariant, but sometimes we have conformal anomaly. So owing to that, there are some normalization can change. So this is a metric with exponential 2 phi, but this is just original metric, G AB equal to delta AB, this flat metric. By this Weyl transformation, there are some factor appears, but the wave functional itself is actually invariant. So this is a standard conformal Fuseli result. But what we want to propose is that this normalization factor is actually represents the degree of freedom and how and actually measure how we do the path integral and counting the repetition of the path integral. So we want to claim that we have to minimize actually this quantity. So this normalization with respect to phi, and so such that always we end up with fine graining in the UV. So this is our proposal. This is the main part of this 2D CFT formulation. So then, so we have, in other words, so we actually think about this functional, which defined by this way, and we minimize it, and then this should be correspond to some measure of size of path integral, and we claim this is actually computational path integral version of computational complexity of this state, which we have in mind. So then, in 2D CFT, but there are nice story. This is a quite well-known story that in so after Weyl transformation, so how partition function or this path integral measure changes. This is given by Liouville action. This is quite well known. So this I phi is just identifies the Liouville action itself. So Liouville action takes this form. So central charge times this integral. And interestingly, these are, of course, two parts, kinetic term of phi, and also this so-called Liouville potential. Liouville potential term is interpreted as just volume of this, actually, this curved metric. So using curved metric, we just measure the volume. So this is obviously proportional number of tensors. Actually, because of one unit cell, we assume one tensor. So this is counting number of unitaries or disentanglers. And also recently, as pointed by Bartik in a nice paper, actually this kinetic term also have a nice interpretation of tensor. This is identified, can be understood as isometries, number of isometries. And that way, so we have some nice correspondence between complexity and the counting number of tensors and this measure of path integral. So this is something. So, but already, of course, wave function is proportional to the exponential of Liouville action. That says that this should give some corresponding size of path integral. But anyway, we take this Liouville action and minimize this Liouville action with respect to phi. Then we get hyperbolic space indeed. So this is exactly corresponds to the shape of this mirror diagram says, but including all coordinate system. So we have this nice. So we have a nice agreement between this time slice of AdS3 and this optimization of this tensor network in this sense. So we can, so this is summary of this picture. So we have some this very fine grained path integral, but we get rid of many unnecessary tensors, unnecessary part of path integral. We get shape up path integral. This is metric is precisely this hyperbolic space, and this is correspond to this mirror tensor network. And we can just generalize this to a sum field double case. And so this is a case we just have some two boundaries. So there are two CFT, this final temperature and beta of 4 and beta of 4 plus beta of 4 here. And we shape up, again, this optimization, and again captured by Liouville action, and we get this value of this wild scaling factor. This gives a precise metric of time slice of BTZ black hole, which is, in other words, this Einstein-Rosen bridge. And also we can talk about the excited state. So vacuum state, we can talk about some analog of some CFT on the circle, which is dual to global AdS. And then after optimization, we get the Poincare disk. This also again from Liouville theory. It's the standard result of Liouville theory. But we can also act some primary operator and excite the system. Then we insert some operator at the center of the disk. Then, so this is, if we assume this is conformal dimension h, it scales like exponential 2 minus 2h5 because it's a scaling mode, wild scaling. So operator should scale this way. And then we minimize not only Liouville action, also with this external contribution. So then we need to solve this equation. This is also well studied in all the literatures. And so in the end, we get the same, looks like same metric, but we have some non-trivial periodicity about theta direction, angular direction of zeta. And this is, it's like 2 pi a, and this is not 1. That means there are deficit angle. And if we assume some large C expansion, if we central charge is very, very large, so this agrees with AdS CFT prediction also. But if we want to understand a higher order correction, so we have to replace this Liouville theory with a classical Liouville theory with a quantum Liouville theory. And then we can have a nice precise agreement. And the Heurich summary, so we excite some, we pass integral, we excited some one point. And but we can coarse grain quite a lot, but we have to capture information made by this excitation. Excitation has some information. That means this excitation back reacts the geometry. So we have some more, we need a more fine graining. And that means we have a larger metric here. And this is captured by the previous argument indeed. So this anyway provides some back reaction mechanism in general relativity, and in this tensor network formulation, at least in this special examples. Okay, so, and we can compute the same thing for also to calculate entanglement entropy. And to compute entanglement entropy, we have to deal with reduced density matrix. And the reduced density matrix given by this path integral with some one cut, some one slit here. And one slit here. And then we do optimization. That means we change the metric so that the metric shrinks. And in the end, we find that metric actually given by this. This one is we paste this upper wedge, upper circle, upper half circle, and semicircle, lower semicircle. That in the end, we just 2 copies of this Poincare disk. So we have some 2 copies of this half. So it's a region surrounded by half circle. This is a very famous entanglement wedge. We get some 2 copies of entanglement. So we can get some optimization. So from this reduced density matrix, we get entanglement entropy. We can do the computation of entanglement entropy by using this formulation. In the end, entanglement entropy computation is equivalent to putting some boundary Liouville potential, and which is proportional to 1 minus n. N is this replica method. We have in my replica method, n is power of rho a. And in the end, we end up with just contribution from here is the integral of exponential phi. This is exactly the length of geodesic line. And this precisely produces the expected formula in holographic entanglement entropy. Okay, so I'm running on time, but this is AdS2, so this is we have lots of interesting development of SYK model, but we can do the same, we can apply our optimization method for SYK model because in addition to this potential term, we have some this Schwartz derivative contribution which come from conformal anomaly. They are indeed compete with the other, and we get a nice solution. We can do the nice minimization. So then we get we can have some time slice of AdS, which is of course just line. And finally, just quickly mention the higher dimensional version of this. So this is a kind of our proposal, but we'd like to optimize this wild mode. We only consider some optimization of this wild mode. And then, and just generalizing previous Liouville actions, most natural choice is this functional. So this phi is this while mode. And this is naturally satisfied that if we take d equals 2, it end up with Liouville action. So this is actually, we can just rewrite in terms of standard Hilbert Einstein action with cosmological constant with this background. But the reason we get the Liouville action is important here is that d minus 2 factor appears. So this gets divergent, but it's cancelled with this exponential. So we get phi times each scalar contribution. So they get so nice connection to Liouville cell. So that, and so these are the properties that this reproduce correct ground state, and nice correct entanglement entropy. And we can talk about first order mass perturbation, and we can capture some divergent structure. We can evaluate complexity itself like this. And this is a kind of generalization. It's very similar to entanglement entropy scaling, but it's one dimension higher. We get the volume law instead of area law. And there are nice works by Rob Meyer and collaborators and Simon Ross and collaborators, and we might be able to compare them. And finally, just to mention that they're also already introduced, so the very interesting conjecture made by Brown and collaborators. So then we can particularly choose this metric slice. So this is a kind of, when we assume Einstein equation, this coincides with so-called Wheeler-DeWitt patch, the region surrounded by this causal now right cone. And so if we plug this metric in this Einstein-Hilbert action, and indeed, it coincides with our action. But up to some factor, and this is actually serious if we go to d equal 2, because this factor goes to 0. And this is exactly the reason that we get a Liouville action. Liouville action, to get a Liouville action, we need this kind of cancellation of this factor, d minus 2, and this exponential. So this might suggest some interesting interpretation of this holographic complexity. And so these are my summary of my conclusions and future problems. So the time-dependent background to understand fully how this is really related to AdS-CFT, then we have to understand time-dependent background and sub-AdS locality and maybe some DS-CFT. But thank you very much. I think I will stop here.
So a very naive concern for getting Einstein's equations out of this optimization is that the Einstein's equations are sort of inherently, fundamentally having to do with the dynamics, with the time evolution, whereas it looks like this optimization, circumvented that, just optimized on a slice. And so how does one hope to sort of, without actually getting a covariant description which would be valid in fully time-dependent setup, hope to extract the dynamics?
But anyway, if we look at just, quantum state, that is time slice, correspond to a particular t equals 0, but that has an information of the whole RG flow, because it has some, if we look at just ground state wave function, like Miller diagram, we can have lots of information from UV, also IR. And in following from this standard idea of AdS-CFT, UV and IR exactly extra dimension. So that we can capture the information for this radial evolution by looking at the quantum wave function. So I think it's quite natural to get a constraint from.
But one gets both just the state, which is the extra dimension, and the dynamics.
Yeah. So but this is focused on static state. We might talk focus on static state. So we don't see time evolution, but we can capture some radial evolution.
But you are hoping to get the Einstein's equations, the dynamics
in Zen. So this is indeed this question, and we have to understand GTT, calculation of GTT component to precisely understand it. Yeah.
Other questions? Thank you.
Yeah, so indeed, if we talk about some excited state, and this, we have some excited state created by primary operator conformal division H, then we need to take some H over C expansion, and to capture this H over C expansion, we need to actually treat Liouville field as a quantum field. And that suggests that we start with, so we actually have to, originally I formulated in terms of optimization, but just minimizing Liouville function. But we can realize it by path integral over also Liouville field, as you also suggested, like some quantum, some Liouville cell coupled to some matter. But that has a yeah, but here it's somehow weight is opposite. We have to think of exponential s instead of exponential minus s. And it's a little different from standard 2D gravity. So that's a very important question, and that's kind of we are trying to understand better. But my talk is so far focused on only a leading term of large C expansion in that sense.
Other questions?
For the minimization procedure, is it important that the tensors are unitaries, or could they be some more generic tensors?
Sorry, second.
So you want to represent, when you represent the state as a tensor network, you could use either unitary tensors or isometries and so on. But maybe you could consider tensor network built out of tensors and not particularly unitary. So it's not cannot be viewed as a unitary transformation from a product state to the final state. Does this play any role in your discussion, or is it important for you that you use one kind of tensor or the other, or is it not important?
Yeah, thank you very much for the question. So, but anyway, this definition itself is just based on the discretization path integral. From that viewpoint, we cannot distinguish this tensor as unitary or not unitary. So it's we expect more we have some more symmetric way to define complexity without relying some explicit construction of tensor and so on. But just so far, we have some consistency check against standard tensor network of NERA, just assuming isometry and unitary. But we should expect more general correspondence. Thank you.
Other questions? All right, let's thank Tadashi again.